that you remove the little bar thing.
No. All right. Any questions from homework?
Number 4, please. Number 4. Number 4.
Really?
1 through 4.
I was a little embarrassed about assigning that one.
What is that supposed to mean?
Homework number 4. Now homework 13. How's parking today?
Awful. It's always that way. UNLV, don't you say?
When I went to school here, guess how much it cost for parking?
Free.
Free.
What? Woohoo!
Oh, no way.
It's okay.
But they don't have those
It costs
parking
more
garages.
to get a ticket for not paying for parking.
Might as well not even start the video till 10 after. No one's playing with their phones, right?
Playing Pokemon over here, so.
All right, so seriously, you need me to do this one?
I need you to do the problem that is similar to the quiz.
So which one you want me to do? This one or this one?
NMOS.
This one?
Yeah.
It doesn't matter. I don't care. Whatever one you want me to.
NMOS.
I already did this one?
When?
With the wire. I'll just do this one. I don't care. I can do both. Here, I'll do this one first. It's not like someone's going to come in late and turn in their homework, right? What the hell?
You just called it. The elevator was late.
Yeah, it was late.
I was calling the elevator.
Now, you know professors never show up late,
Whoa.
What?
That's an April Fool's joke.
so students should never show up late.
No, that's Dr. He's late 10 minutes every day.
No, he's not. What was today's homework? Was it tough?
Yeah.
All right, is this the problem right here? So this is the current flowing ID. What's the VGS here? So what's the DC current that flows? All right. Why would it be in triode? The gate and drain are at the same potential. All right, so let me see if I can estimate what that is without a calculator. So this would be 60 times 5, so 300 micro, times 4.2 times 4.2 squared. So 4.2 squared is 16 plus, what is that? 0.2, 0.8, 7, about 17 point,
160 plus 16.
I'll say 17.16. I did that right? Yeah, we'll just say 17. And then that times is 300. So that would be 510. Right? Oh, it's 5,000, 17. Oh, yeah, 5,100. So ID equals 5.1 milliamps. Can I get a second on that? Did anybody get that in the sim, roughly? How? You keep saying triode here. What?
Well, we made our own ideal MOSFETs to make it right.
You guys are talking crazy talk. What's this voltage? What's this voltage? How can it be in triode?
That's
With your own made-up models that you built? Are you going to waste my time? I'm going to go over to the sim and it's going to show that this isn't 5 volts and that's not 5 volts?
No, if you run this sim, you'll
Yeah, but remember that you expect them not to be exact, right? I mean, there's all kinds of secondary effects that go into that. So that's what my hand calculation was. Now what? GM. Well, wait, does anybody not follow this? I mean, I'm not understanding. You guys are like, oh, this is hard. And I'm like, what? It's easy. Then I'm looking at it going, okay, you're losing touch with reality. I'm looking at it, I'm like, So anybody not follow that? So what is GM then? Everybody agree with that? 600 times 4.2 is roughly 2.4 milliamps per volt. All right, and so what's the AC voltage here?
1 million? 1 million.
So what's the AC current then? Boom, done. Yes?
I can have number 2 as well.
You're killing me, man.
I want to see if I did it right.
Really? Hold on. Question, what's your question?
I was just going to ask what we diode connected stuff in the past. We didn't need the resistor, so I don't understand why we.
The resistor means it doesn't load. You can't get an AC signal from the output back to the gate. So for AC, that resistor makes it an open between the gate and the drain, but then it biases up correctly. All right, what's the VSG here? 5. So what's ID? DC? And what was this, 30 by 2? And what is GM? Am I given enough homework? And then what's ID? Boom, done. I apologize. These were absurdly unchallenging problems, and they probably insulted you. Tell me, am I wrong? Now that I've done them, they're easy?
Yeah.
Yes.
So in that case, what we know is that there is no current flow through our right? Because we have potential.
Yeah.
Potential up to.
Other than you realize that ROP is a model for the MOSFET, so like you got 2 milliamps instead of 5, there's that issue, right? Because the current doesn't do this, doesn't go up like this for ID versus VDS, does this, right? And then it doesn't, it's not, the other big thing is it's not VDS SAT is not VDD, it's not VD minus VGS, I guess, if you want to say that. Oh, wait, let me see. VDS out. VGS minus V threshold in. It's not that, right? Because it's less than that. Because the voltage at the drain will attract the electrons and cause VDS sat to be less than this. All right, any other homework questions? Actually, it was like, should I give them such an easy problem? And then I'm like, I don't understand how that works. I'm like, okay, I didn't think we had to specifically say the AC voltage is 0. It's actually shorted to VDD and ground, but okay, if we need to say that. Yes.
So what in the simulation, I know in the calculation we get for ID, like about 5 milliamps, but in the simulation you
Well, I just went over that.
Yeah, you say because of that.
Because of what?
That the threshold voltage changes as you increase VDS in this case also?
No.
No.
But remember, the threshold voltage is going to be a function. Well, wait, let me back up. We're getting too hung up on secondary device physics. So here I've grounded the gate and the source of the transistor, right? And then I'm going to start sweeping this voltage. Refresh my memory what happens. Electrons get attracted up there. And what does that do? What was the fancy term that's called where we've got electrons up in there? No. This is off. There's no channel length modulation because it goes off. Drain-induced barrier lowering. And so I've got these electrons attracted up under there. That's what I'm going to do, and then that influences the threshold voltage, right? And so it'll change what the actual calculation, but there's a whole bunch of other things that go on. That's why I have to use the models. Here, let's make sure. You guys are killing me with this because I thought I went over this well enough. Let's go back to chapter 9, and I want to put up a figure. And I really want to understand this because you're like, oh, it's off by a factor of 2. I must have done something wrong. Let me waste time and make my own model so that it works and it matches my hand calculations. Look at this figure right here. Remember when we derived this, or we simulated this, and we went through this in chapter, why isn't that working? Remember when we went through this in chapter 9, and I said, look, we calculate a VDS sat, and there's where it is. But now notice that when we start to change VDS, what happens to the output resistance? If I increase VDS, what happens to the output resistance? If I increase VDS, what happens to the output resistance? Don't answer before looking. Increase VDS. Here's VDS. I go from here at, say, 0.1, and I go up. What does it do? Gets big. So say here I'm at 10K, 20K, and then I say, hey, I'm going to increase by a little bit, 0.1 volts. Boom, I go from 10K to 150, off by a factor of 15. Well, I'm going to spend time redoing my models, and I did something wrong, obviously. I don't know how much clearer I can be here. These are real devices, and they've characteristics change. So if you're going to spend time wasting on, hey, when I go up here and I go to this voltage, and I go down here, I'm doing something wrong, that's not a reasonable use of time. Does everybody follow that? It's not magic. I'm not making this up. There you go. There's one example. And you're off by a factor of 2.5. What if you're off by 15? All right, any other homework questions? Let's talk about Miller's theorem. Before we do that. So one more time, does everybody understand that if your hand calculations aren't precisely the same as your simulation results, that's absolutely expected. If they're precisely the same, you did something wrong, or you're using the level 1 model. Remember, I put the level 1 model in, and I got exactly what my hand calculations were. So if they're not different, you're doing something wrong. Is that clear? All right. You know what's in my mind right now is they're spending like 10 hours every weekend working on these homework assignments that are meant to take 2 to 3 hours because they're second guessing themselves. All right. Let's go here. This is the next homework next week, not the one that's due on Wednesday, the one that's due on Monday. Oh, I clicked on 13 again. This is the one I want.
What in the world? Oh my God.
That's what I said. Next, not this one on Wednesday, but the one a week from today is on frequency response. Now, I'm going to go through frequency response today, but we have to get to the point where you can do your projects, and we're pretty close to being there, but I don't, those two problems you ask me homework, it scares the crap out of me, honestly. I'm like, uh-oh. All right, so here, these are frequency response problems. We're going to go through this first one right now, Miller's theorem. And if you took 421, 621, you've already seen Miller effect, but I'm going to go over it again from an analog point of view. So, and I'm going to explain it qualitatively to begin with. So I have an amplifier with a gain, minus A. Give me an example of where you would have an amplifier with a negative gain. What kind of topology? Common source amplifier, correct. And you've been calculating lots of gains, right? Today's homework, right? All your gains were negative for the common source amplifier. So I'm just going to label that as minus A. And now I want you to look, and I want you to think about this. When the input goes up, and it goes up, let's just call it V in. All right, everybody agree with that?
Yep.
What does the output do?
Go down.
Goes down by how much?
Well, that's a capacitor.
A times V in, or minus A is what it goes down to. Does everybody see that? So if this was 1 millivolt, and this had a gain of 100, this would go down to minus 100 millivolts. So now if I look at the voltage drop across the capacitor, this side's going up a teeny amount, this side's going down a large amount. When I have a large voltage change across the capacitor, what do I think happens? Get a big current through the capacitor. Okay, so what I'm going to do is I'm going to apply a test voltage here, V in, and I'm going to call this V in. And then I'm going to ask, what is V out? And you say, chuckle, chuckle, you're not challenging me. It's minus A times V in. Oh, come on. What's going on with my camera and all that? All right. It's doing that last 2 times, right? It did it in circuits too. I would say defrag the hard disk, but I specifically bought a solid state drive, and that's the last thing you're supposed to do to a solid state drive. Why? Yeah, write endurance. It's how many times you can write to this flash memory is, and if you start defragging your hard disk, you're going to be rewriting and moving things around, which will wear out your solid state drive. All right, so what's the current through there? We'll call it I. What?
He's worried about his computer now.
All right, what's the current?
DVDT.
Correct. V in minus A times V in all over 1 over j omega C. This voltage minus this voltage over that capacitance.
Oh, this is AC. ADC.
And would everybody agree that's equal to V in times 1 plus A? And why don't we put this in absolute just to remind ourselves that A has to be a negative number divided by 1 over j omega C. Looking good? And what I'm going to do now is I'm going to write V in over I is equal to 1 over j omega C times 1 plus A. And I'm going to tell you that if I break this capacitor and I put a capacitor here of 1 plus A times C, I will get the same current I flowing in that capacitor as what I had here. This is called Miller's theorem. So if I had a gain of 100 That means the input capacitance here is going to be 101 times C. In other words, that common source amplifier is going to take that capacitance it has here, multiply it by 100, and then I'm going to have a huge input capacitance. Remember last time when we went over source followers and we talked about how small input capacitance was desirable if you're sensing charge, for example? And so here, that's not good because I've got a huge input capacitance. Any questions? Okay, I also have a capacitance on the output of C times 1 plus 1 over A. And I want you, all I need to do here to prove that is, and I'll write it here, is V out over A, and this is V out, and I can do the derivation and go back and get this. This is the Miller's theorem for the output. But if I look at the output using Miller's theorem, so once again, everybody follows. I'm taking this capacitor and I'm breaking it into two components to model the current that goes into the capacitor. Any questions? One's equal to 1 plus A. Is that capacitor really here? No. That capacitor really here? No. I'm using this equation for analysis. And so why is this, just tell me very clearly, why is this capacitance much smaller than that input capacitance? I want you to explain to me why that's the case. Well, let me ask a simpler question. What can I say about the current through this capacitor, here I, relative to the current flowing in that capacitor? So this one flows in like this. So I'm breaking that capacitor up and I get this current flowing in the input capacitance and this one being pulled back to the output of the amplifier. Why is this one smaller? Or wait, what's the relationship between the currents? They're equal. They better be. The same current flows in the capacitor. This current flows in here and into the output of the amplifier. This current flows in here and into the output of the amplifier. No? All right, let's do it again. It's poor quality instruction. I don't know why this is, I guess I do know why. This is a tough concept. So the gate of my transistor doesn't pull any current. I'm not taking into account its capacitances. This is my V in, this is V out. And I start to wiggle V in, and then V out is equal to minus A times V in. So far, so good? Current, AC current flows, goes back and forth through here. Just like this, and I call this current I. Okay, if you tell me it doesn't flow into the output of the amplifier, my question is going to be, okay, really? Then where does it flow? And you're going to find when you make your op amps, you have to have transistors here that either source current, which means they push current out, or they sink current, which means they pull current in. So all op amps or digital gates, you don't see this, but it sources or sinks current. Here it's sinking current. Does that make sense so far? You see how the current I flows in the output of the amplifier. What's the current that flows here? I have no current flowing there. But my output has to be able to drive. If it doesn't, then how do I listen to music on speakers? Because my audio amp has to be able to drive the speaker. That means it has to push current into the speaker and pull current out of the speaker. Ready to move on? Then we said, okay, where we're going to model that current is we're going to do the following. We're going to put a capacitor here of C times 1 plus A. And here we have a capacitance of C times 1 plus 1 over A. Now let's go back to my questions. This current that flows in here I'm going to represent to you is I. What's the current flowing in here then? I. It's got to be the same thing, but I'm modeling the currents there with that I. Does everybody follow that? The currents are equal. So now back to my original question. Why is it that this capacitance is going to be basically for A large, C? It's going to basically just be the C, whereas this capacitance is going to be much larger. Oops, I did have a bracket there. What was I doing? Why is it? Small electrons? What? You're tweaking me, man. Don't tweak me. It's April Fool's Day. You're going to give me a heart attack. Well, this has smaller electrons,
Well,
so.
the capacitance because the voltage is a much.
Yeah, right.
Change.
This is a little voltage. This, you need to know this. This is a little voltage. This is a big voltage. So to get the same current, I need a smaller capacitance over here. Everybody got that? Okay, so now I want to use this as an example. I want to use this theorem. Any questions? All right. Let's go and call this V bias 1. And let's go to a PMOS. That is 30 by 2. And let's have our NMOS here. And then I'm going to have a capacitance here of 10 picofarads. And then I'm going to have a 100K here. And let's put a capacitor there so we don't mess up the biasing and our big resistor and all that. And I want you to first tell me what, let's just do it from memory. V out is equal to V in at low frequencies. At low frequencies, what is the AC voltage here? Or let me back up and ask even simpler questions. What's the DC current flowing in this topology from our long channel MOSFETs? 20 microamps. So what's the DC voltage right here? 1.05. What's the DC voltage there? 3.85. At this point, I'm not giving you enough homework if you don't know those. Okay? So then I ask, well, let's ask a simpler question. If I don't have the 100K resistor, or let's even ask a simpler question going back. What is V out in terms of V in? It would kill me if you can't derive that at this point. Oh, before I forget, on the quiz today and Wednesday, I put closed book, and then I realized I don't want these to be closed books, but I want to reprint them. I fixed the PDF I'll post online, but when I hand this out, they're all open book, even though it says closed book. I don't know, man. What? All right, anybody not follow this? All right, so what were R out? What was the gain here from your? Does that ring a bell to anybody?
Yeah.
Is anybody reading the book? Okay, I don't want to spend time on that. 333. So now I'm going to redraw the AC schematic. Note that, and I'll change this in a moment, the 10 picofarad here is much larger than the device capacitances, so I'm not including the device capacitances. I will in a moment, because that's not always the case where the capacitance is much larger. So would everybody be okay if I wrote this as 10 picofarad times 334? And then on the output, I wrote this as GM times VN, or actually, let's write it V, let's call this V source to be consistent, VN, and we'll just write it as VS for now. But it's actually going to be changing, and then this would be the 5 in parallel with the 4, and then I didn't do a good planning for my layout, but then I've got a capacitor here that is roughly 10 picofarads. Everybody follow that? I'm just going to leave it at, it's actually, yeah, let me be right, VN. All right. Any questions how I broke that 10 picofarad up using Miller's theorem? Okay, so I've got, the reason that I did that should be obvious now. I get 2 time constants, which will result in 2 first order circuits, which will result in 2 roll-offs. Okay, so if I look at this, I'm going to ask some questions. But before I do that, are there any questions from you? So this transistor is this current sink here. This 5 meg in parallel with the 4 meg is this output resistance and this output resistance. This node here is V out. So I got a transistor here of 4 meg. Got a resistor here of 5 meg. And then my transistor has a current of GM times Vn. And so this circuit here, when I break the capacitor, I've just redrawn over here. Then on the input, I have my Vn, my big capacitor is an AC short, then my 100K, and I've got my Millerized 10 picofarad here of 334. Looking good? Now you can see why I did that. I got 2 separate circuits. I could Thevenize this into Vn times 333 and then the resistor if you want. Maybe I should do that on the next page because some of you I have concerns about your circuit skills. So let me do this the one time. So So 334 would be 3.34 nano. And then over here, I would have Vn times minus 333. And then a resistor of 4 meg in parallel with 5 meg, which equals what? Isn't it 4 times 5 is 20 divided by 9? Oh, it's 2.22. Okay. And then here I've got my 10 picofarads. And so what is another name for the 333 there?
That's supposed to be a current source, right?
No, that's what I was saying. This is a current source, this is a resistor. I'm Thevenizing those into the Thevenin equivalent, which is a voltage source and a resistor. I'm just doing really simple stuff, but when I say time constant, I assume that you can go from here and know the time constant's 1 over 2 pi, the 3 dB frequency is 1 over 2 pi RC. And I cringe and I'm like, can they really? Yeah, maybe some of them can. I should cover that. See what the crazy that's going on in my head? All right, everybody follow that. And of course, I'm going to sim this. And we're going to see some issues. So what are the 3 dB frequencies? Let's call it Fn. Does that thing keep freezing? What the hell? It's probably Cortana. How do I get rid of Cortana? Why is the visualizer taking so much CPU? Anti-mal services. What? Something else is running. Oh, now it's not.
Yeah, you have two.
Really? Yeah, is anybody using these videos? Yeah. See? No, you know what I think? Because I had problems with this, I uninstalled it because of the bar thing. I'm wondering if it really uninstalled, because the one time I installed it, it was a add-on in Chrome. Use the whiteboard? I hear you. No, use PowerPoint instead. Okay, F out is equal to what? Should I get my calculator out? Yeah. You guys are slow. Somebody fast, do it. Beat me. Prove me wrong. 6.28 times 1 shift E. Oh, whoops. Yes. $477. 72 kilohertz. So 1 decade above 477 is 4.7. 2 decades would be 47. So these are apart by more than 2 decades. Let's now sim and see what the sims say. Expect a really low frequency and then one that's pretty low, but not really, really low. All right, we ready? All right, let's 7.2K. Is it 72 kilohertz or 7.2K? What? Oh, 7.2K. All right, so I guess it's off more than a decade, but not 2 decades. We'll see. All right, so let's pull up one of these. There we go. File, save as, and then let's go over to lecture 16, is it?
Yes.
And then let's go get out the scissors here. And then let's go. Get rid of this. Move this stuff over. Stretch this stuff up. And let's get out a little capacitor here. And what's the value? And let's put it in. Now let's get a voltage source here. No, I need the resistor too, don't I? Does it matter which side of the voltage source I put the resistor?
Yeah.
Does not. What's that? And the value of the resistor was 100K. That capacitor will leave there at 1, not 1F, because we don't want pain. Oops. And let's hit save, and then right-click here.
The resistor on one, wouldn't that make the gain negative 1 billion over 100?
No, because the 1 gig is much, much larger than the 5 meg and the 4 meg output resistances. So if you actually go through and do the analysis, when you're looking at one source at a time, you would short out this voltage. And so neglecting the source resistance, this would be at AC ground, which is in parallel with the output resistance of the PMOS and in parallel with the output resistance of the NMOS. All right, let's put this as 1 millivolt, or let's just put it as 1 because I'm lazy. I don't want to do the ratio. All right, let's hit save, and let's hit, let's do this. AC analysis, type of sweeps, decade, number of points per decade, 100. Let's start at 1 hertz because we're going down to 477, and let's go out to 1 megahertz. All right. Save. I think it's good to go. Roll them. And let's look at our signal here. Boom. Should be, when I collect this, what should I see? Straight line at 0 dB. If it was 1 millivolt, what would it be at? Minus 60. 20 log of 10 to the minus 3. 1 millivolt. Then I'm going to go look at my output, and I'm going to look and see, and my gain I calculated is, what was it, 333? Yeah, 333. Does that look close? Looks a little low, right? How do you know it looks low? What's 40 dB? 100. I'm seeing a bunch of blank looks. So let's go to linear. And I look, and the gain is not quite 90, quite a bit less than what I calculated. So here would be good where I could do a dot OP and see what the values are, but it's off by a factor of 3 or 4. Almost, or 5, almost 5. All right, that seems a little bit large, but I don't know where I bias these things. All right, so what do I expect that's going to do to my capacitances and my frequencies that I calculated here? If this is no longer 333, but now 90, what do I expect this frequency to be? If I have a lower gain, what happens to my frequencies? If my gain goes from 333 to 90, what's going to happen to my capacitance? It's going to get smaller. What's going to happen to the 3 dB frequency? It's going to go up by a factor of 5. I calculated 477, so I'm going to expect something about 2 kilohertz. This one's not going to make, it's not going to be different, right? Because I've got my 2.2, and then this is still 10 meg, or 10 picofarads, so I don't expect this one to move too much. So we're going to see some interaction, but let's see. So I expect this one to be a little bit higher, this one not to change too much, but let's go find out. So the first one is roughly at, let's go back to dB. 3 dB, so this is, what is it, 38, so roughly 35 is out here at 2 kilohertz. Does that seem reasonable? Yeah, seems very reasonable because I calculate 477, but now my gain is 5 times smaller, so I expect my frequency to be 5 times bigger. Well, it was 333 versus 90. Oh, okay, 4 times bigger, yeah. Oh yeah, 4 times 477 is roughly 2 kilohertz, right? So I go over here and I say, all right, and then I look and I say, all right, well, what about my next frequency? And I look and I see that it doesn't, so if I look at this, how do I know this is rolling off with 1 pole? Let's ask that, or versus 2 poles. Well, if it's rolling off at 1 pole, what do I expect? 20 dB per decade. So let's go pick a value here. Here's 2 kilohertz. Would everybody agree with that? What? And I've got a gain of 35 dB. What's 1 decade above 2 kilohertz? 20 kilohertz. So I go up to 20 kilohertz, which is right here. And let me pause. How many people follow that when I say decade and I go from 2 kilohertz to 20 kilohertz? How many people follow that? All right, so most of you. So if I go from 2 kilohertz at 35 to 20 kilohertz, I'm down from 35 down to roughly a little bit above 15, roughly 15. Would everybody agree that's rolling off at 20 dB per decade and continuing on? I'm going to simulate it a little bit further. I want to show you something. So let me tell you something and then we're going to cover it. What's happening is that the second pole, which would be the one associated with this one here, is being canceled. And I want to explain to you why with a 0. But before I do that and go into that discussion, let's simulate this out a little bit further. Let's go out to 100 meg. Hit run. And then I look. And I see that out at 3 megahertz or something, that I have a 0 and the frequency response flattens out. All right, so my calculation worked well for the low frequency pole, but it didn't work well for anything else. And I want to, before I move on, does everybody follow what's going on? All right, so here's the issue. If you go back here and you look at the derivation here, let's go back to the first page. Or let's go to this page, this one will work. You see that if I have the, at high frequencies, you see that in the original circuit, the input and the output are shorted together through the capacitor? Does everybody see that? You see in this circuit, we've lost that. In this circuit, we get these capacitance, but we don't have the 0. I'm saying that as if everybody follows. We don't have the situation where the output starts to go up with the input because of the feed through the capacitor. Just pausing for a sec just to make sure everybody's on the same page as me. When I say pole and frequency response, what's in your mind? Goes down, right? If I say 0 in frequency response, what's in your mind? goes up. So if I have a 0 here and I'm going down, what happens? Flattens out. That's what we just saw in our frequency response, right? Okay, so when I use Miller's theorem, I don't have that, it doesn't take into account this 0. Does everybody follow that? All right, so let's talk about that. And this part is a little bit mathematical. And let me show you where we're at in the book so that you can read this too. Does anybody, my circuits class, nobody ever reads the book. And I ask why, and they say, because your lectures are so good, we don't need to read the book. So I'm like, crap. I got to make them read the book. So now I start assigning problems out of the back of the book, and they hate it. And I'm like, yeah, it's good. All right. So,
write your own circuits book?
no, I'm not writing any more books, man. It's so much work, and then people just take it and post it online. And it's like, but it's expensive. I can't afford it. I was hungry. I needed that bread. All right. We won't get into debates here. All right, so this is what we just did. You see this example? This is the example we just went in through where we calculated the pole associated with the input. Instead of using the capacitor, I used the capacitance between the gate and the drain of the M1. But there's also the capacitance parallel with that CGS, and you can look at that here. Here's the CGS and here's the capacitance, and so this is a little bit more detailed description of the input pole, and then you recognize what's this part right here. That's the gain or the output, the Miller associated, and there's your output resistance of 1, output resistance of 2, and then there's your capacitance in parallel with that I've got going to AC ground. And so I've taken this gate drain capacitor, I've Millerized it, and here's my equivalent circuit. And if you go through the example, what you're getting is that your F out, we just calculated, is wrong, right? We just calculated 7 kilohertz, and we looked at it, and it wasn't at 7 kilohertz. So here's what we're going to do. You see this circuit right here, this one down here? This is the one we're going to spend all the time on in the rest of the semester, because this tells us how to do compensation. And I want to explain a few terms, and then I would like you to read through this on your own so that when I go over it next time, you're not seeing it for the first time. But the most important thing is this pole splitting. So read 676 through pole splitting summary, because these are the equations you'll use in your project, and these are the ones we'll use for design. All right, lots of algebra. But I want to qualitatively explain what pole splitting is. All right? Because I think understanding stuff and then doing the math is good. Okay. So if I look at my amplifier here, I'm going to try to explain this qualitatively so you know what's happening. If I look, this is the capacitance, and then I re-sketch it so that the capacitance value is C times 1 plus A. And then on the output, the capacitance value is C times 1 plus 1 over A. Everybody agree with that? Well, what happens when I have my input resistance driving this to the input voltage here in the amplifier? As I start to go in and this capacitance takes hold, what happens to the amplitude of the input here? It's going to go down. Let's see. So I got my V in here, and I've got my Miller capacitance. So I go back, and I look at my simulation, and I say, okay, well, I want to run the simulation. Now I'm going to look at my V in here. Actually, let's pause and redo this. Call this VS. Let's call this VS. Yeah, let's call it VN. I hit run again, and then I plot this. What did I just do?
You shorted the VNs.
Oh, I had a brain fart. This is VS. And I hit run. And then I do this, VN. And I look at VN, it starts to decrease down here at, what did I calculate? 400 or whatever. So it starts decreasing. So now let me go back and explain what's happening. So if I ask, VN is starting to decrease, right? That causes V out to start to decrease as well. But from an overall point of view, this VN here, this VN is staying the same. But here, I'm seeing this signal go down, and thus effectively this A is going down. Because from here to here, I'm seeing a decrease in overall gain, A. Because I was using A at the low frequencies for this, but as I go higher and higher frequency, this A starts to roll off. What that effectively does is cause this capacitance to go down as frequency goes down. And if that happens, what does it do? Well, it pushes this pole associated with the input out to a higher frequency. What's that? I'm sorry. Yeah, sorry. Thank you. Frequency's going up, right? And that causes this to effectively look like the capacitance is getting smaller as the frequency goes up. And what that does then is this pole associated with the input then gets pushed out, or splits away from the pole associated with the output. So that's called pole splitting. So let's look at that again. If I go back over here and I say, okay, if that's the case, then this pole is being pushed out. And I look, if I put a capacitance here on my output, let's just put, let's put one here, 100 pico. Okay, so let me repeat. Does everybody understand that as the gain of this amplifier starts to drop, this effective capacitance here starts to drop, and the pole associated with the input starts to increase, go to a higher frequency? So let's see what happens when I put the 100 picofarad in here. And before I do that, let's go back and plot. Oh, it's already there. There's V out. Now, keep your eye on that. And now you see my low frequency pole went down, and then I've got some interaction, and my frequency response out here is doing something. But the key takeaway is this frequency went from up here at 2 kilohertz and went down. And that's because I've loaded the output with more capacitance. So this pole is mainly due to the output. Did anybody follow that? Kinda? All right, let me look at the equations, and then we'll do our quiz, and then we'll pick up here next time. Yes?
We added the 100 picofarad to see
If I can move the pole associated with the output, because 100 picofarad won't influence the pole on the input, right? It will to some degree, which we'll cover in a little bit.
100 picofarad to like maybe 1 pico.
It would move it back to where it was, effectively. Okay, so, all right, so real quick. So here's the circuit. And while you're taking your quiz, I'm going to play with the IPEVO visualizer and make sure I get it all uninstalled. Use the what? I couldn't find it installed anywhere, so that's why I uninstalled it in Google, because it was an extension, and then I reinstalled it without using Google. So, well, we'll see. Yeah, somewhere. I'll look for it. I checked the program files. I didn't see it, but who knows. All right, so here you see, yeah, you know what? This is the model. Let me just hit the high points. There's 2 poles associated with the transfer function that we'll go through, and a 0. And the 0 here is troublesome because that 0 is located in the right half plane, and so its phase shift adds like a pole's phase shift. In other words, adds delay rather than a normal 0, left half plane 0. And so it's very troublesome. So there's the 0 location. Here's the first pole location, and you should recognize this term as the Miller capacitance. And then here's the second pole location. And so here's the overall transfer function. Again, note that the 0 is minus here, and that's located in the right half plane. And where did I say that? I said that somewhere. Oh, so much work. All right, so that would be the 0 location. I don't know why I don't see it in here, but it should be say it's in the right half plane, and you can see in the discussion here the negative that adds to the phase shift. Why don't we stop here and then we'll pick up where we left off, and I'll go through the derivation next time.